And we are now recording. Let me get my slideshow set up from the current slide. I think we already went over this slide before last time, but before it comes up, or while it's trying to come up, two announcements that I know of this week. Both of them have to do with office hours. Tomorrow I've got a doctor's appointment, and my wife told me the time early in spring break week, and then I've forgotten what it was, whether it's 11:20 or 11:40. But what it boils down to is I normally have office hours from 10:45 to 1:15. Basically, most of those office hours are going to be gone because I'll be at the doctor's office before 10:45 because I've got to do blood work before about 10:20 or 10:40, something like that. And then the doctor's visit is going to last probably close to an hour, especially late in the morning like that. And so I'll be pushing it to get back here by 1 or 1:15. So almost all my office hours are going tomorrow. On Friday, normally I'm on the Birmingham campus, 7:45 to 1 o'clock. I've got an infusion scheduled then, and that's going to be, it's scheduled for 8. So I'll probably have to be there by 7:45 to, get everything running, and it's going to be all day. So it has been the last several times. So I don't anticipate any difference this time. So basically tomorrow and Friday, almost no office hours at all. Now, do you remember or recall seeing what I meant to look it up while I was down there, when Honors and Awards Day is? Isn't it next Thursday, not this coming Thursday?
Can I have the email? I don't remember exactly the date, but somehow it's on Thursday.
I remember, I think it's a Thursday, I believe it's the 12th, but, I'm sorry, that would be the 13th. It's either this Thursday the 6th or next Thursday the 13th. I just don't know which. Yeah, that's all right. We'll find out. I don't think it'll affect this class any, but all right, let's go from there. All right, I think we covered this slide before. Any questions before we get going? Okay. And we might get to this slide before it's over with. Yeah, we will. So I might as well start with this slide. Example 2 on page 690. This is chapter 13, 13.1. Example 2 is a helix. Describe the curve traced by this function, r of t, here we go. Let me get my pen redone. Okay. R of t, it's a vector function, minus sine t, cosine t, 1. No, t. I'm sorry, t. Okay. And this is for all t greater than or equal to 0. Okay. It says, describe the curve traced by this in terms of its projections onto the coordinate planes. Okay? And they've really shown it to you already. Okay? But let's pretend it wasn't there. Let's start with t equals 0, because that's as low as you can go. What is sine of 0? 0. So the x coordinate starts at 0, negative 0. So x here, 0, you're somewhere basically on the y-axis, because x is 0 everywhere on the y-axis. Cosine of 0 is 1. So you're on the y-axis, but you're over here at y is equal to 1. So that's where we're starting, okay, or right here. X equals 0, y is equal to 1, and z is equal to 0, okay? So you're not up or down, so we're starting here. And then as t increases, sine first goes negative, so your x is going negative, going back this way. Negative x is into the board. The cosine is also decreasing. It's going negative from 1, so it's going down to here. And then it continues going like this, but all the time t is increasing, so you're moving up the z-axis. And that forms a helix. Now, that's the description of it. Let's look at the projections onto the various planes. Onto the xy plane, that forms a circle whose coordinates are minus sine t, cosine t. And exactly like we see here, just starting here and going around and around and around. Okay? On the xz plane, the plane here, xz plane, starting at x equals 0, z is equal to 0, and then it goes like this, back and forth from, it basically is a sine curve moving up this way. Starts at 0, goes up to 1, down to 0, down to 1, and like this. So that's exactly it. I mean, sort of like what it is doing here. Okay? On the YZ plane, the one back there, is starting y is equal to 1, z is equal to 0 because t is 0, and then it's going up here, crosses, of course, above the y-axis here, goes over to minus 1, back to 0, back to plus 1, and down. So again, it's acting sort of like a cosine curve, because if you look at it, that's what it is, projected onto the xz plane. It's just that it's acting like that, but it's not exactly a cosine curve, but it's pretty close to it. All right, so that's, I think, all they were looking for there. Now, when I said minus sine t, cosine t, that's treating that as 0, okay? And that's why you do this. And minus sine t, that's basically a sine curve, but it's not just a sine curve, but it's increasing going upward as you go. So it pretty much looks like this. And that one, with this equals 0, looks like a lot like the cosine curve, which of course, that was right. Okay, I guess that's all they wanted. Now, they make a statement here which is pretty good. Every curve can be parameterized in infinitely many ways. So anytime they ask for a parameterization of a curve, don't think you have to get just one answer. You could have several. You just pick the ones that you think would be best, because there's infinitely many ways a particle can traverse a curve as a function of time. The next example describes two very different parameterizations of the same curve. And that's example 3, and I don't think they have, yeah, I guess they are these. Parameterize the curve C obtained as the intersection of the surfaces x squared minus y squared is equal to z minus 1. That's this curve right here. X squared minus y squared is equal to z minus 1. So if you look at that, and based on what we did in the last 12.6, okay, this is a paraboloid, because you see one variable is to the first power, the other two to the second power. Because these two have the minus sign in between, it's a hyperbolic paraboloid, okay? Because that itself would be a hyperbola. This or that would be parabola, or parabole, either one of them. Okay, so this would be a hyperbolic paraboloid. Okay, so that's what this one gives you. Now, a little bit different from what we've done before. Before we had the starting at 0, this one starting z is equal, when z is 0, this thing is a difference is a minus 1. In other words, it's y squared minus x squared. That's why the parabola, how to say that? Let's just take with x is 0, y is 0. That means this has to be 0. Z minus 1 equals 0. That means z is equal to 1. So when x is 0, y is 0, z is 1. Okay. So that's what starts you up here, not at the origin. Okay. And then when z is positive, the x, y is constant or y is 0 or however you want to phrase it, z is equal to x squared plus 1. That would be a parabola that's opening upward. And you see, when you look at the xz plane, where y is equal to 0, okay, xz plane where y is equal to 0, you should have parabolae opening upward. Why does this look like they're opening downward? It is opening downward. No, I'm sorry. XZ plane. Okay, that's the XZ plane. Yeah, the parabolae are opening downward on the XZ plane. I think they may have the axis crossed. I think they have the figure rotated because these should be opening upward. When x is 0, then you have z is equal to minus y squared. That would be one opening downward. Okay. So when x is constant, it should be the other way. So I think they have the figure twisted, but not badly. Okay. Marcus is here. Half the class is here now. Okay. Now, the other one, x squared plus y squared is equal to 4, that's a cylinder. A right circular cylinder, radius 2. Okay? Now, the question is, what's the intersection of those two surfaces? Thank you so much. Okay. The intersection of those two surfaces would be, you can see what it is when you plug it in here. Looking down on it, it's got to be a circle, but that's kind of a tough thing to look down on and see. Okay, but you know it's got to be a circle. Looking at it up the y-axis, in other words, say where y is equal to 0, or any other constant, then you should have parabolas going upward. Z is equal to y squared. I guess this is right, yeah. And they're opening upward. And x equals 0 or any constant, you have z is equal to minus y, so those are opening down. So it was correct the way it was done here. Okay. But how do you express that curve? Well, like they said, there's an infinite number of ways, but here's a couple of ways you can approach it. Okay? First, we know both of these things have to be true. So we know that x squared minus y squared minus z minus plus 1 has to equal x squared plus y squared minus 4. those two have to be equal to each other. Okay? Now, one thing that you could do, one way to look at this may not be the best way. For some arbitrary constant, say z, so let's let z equal some constant. And by the way, your z's here are always, no, they're not always positive. But let's just say z is one constant, c. And let's pick another parameter. Let's see, we usually use our parameters to be letters like t, so let's start with t, not c, but t. Z is equal to t, and y is equal to, say, s. Okay? Then your x would be x squared is equal to, let's start with this first one, s squared minus t s squared plus t minus 1. And at the same time, x squared is equal to 4 minus s squared. Okay? And these have to be true at the same time. The x squared is the same in both cases. So s squared plus t minus 1 is equal to 4 minus s squared. Add s squared to both sides, you get 2s squared plus t minus 5 is equal to 0, or is equal to plus 5, or however you want to say that. There is one way to do it. Now let's see what their two ways would be. First method, solve for the given equations y and z in terms of x, and that's really what I just did, only I did with them in terms of x squared. And see what they got here. There, yeah. Oh, they got it in one variable only. Sorry about that. I did two variables. Okay? So we need to do something else to simplify this. I put it in two variables. They only have it in one. Yuck. Okay. Well, they first solved for y and plugged those in. I did it for x, and we could have done that with one variable perhaps. Let's see if we can. Basically, this is saying x squared is equal to 4 minus y squared. Okay, that's one way. That's taken from this one. And then plug that into this one, and you get 4 minus y squared minus z plus 1 is equal to 0, you could say. So this would be 4 minus 2y squared. I'm going to write it this way. Plus 1 is equal to z. Okay. So that would be 5 minus 2y squared is equal to z. So then why don't we let y equal t? Or I think I'll do away with this other since they use t also. Y is equal to t. So z would be 5 minus 2t squared. Okay? And from this one, y is equal to t, x is equal to 4 minus t squared. So now our parameterization would be r of t would be equal to, the x would be 4 minus t squared, the y is t, and the z is 5 minus 2t squared. Okay. Now that looks a little different from theirs. Oh, wait. I messed this up. X is equal to plus or minus the square root of that, because x squared was 4 minus t squared. Okay. That probably going to change things somewhat. No, I think that would be okay. So this is the square root of 4 minus t squared and minus the square root of 4 minus t squared. Okay, that's another parameterization. And it's not far off from what they did. But it just seems like a more logical thing to go with the x's. Maybe it's not, but it just seems like to me it is. But like they said, there's an infinite number of ways of doing this. Now the other technique, or the other thing to do, is, especially if you notice, that's a geometric shape there, right? The circle, okay? When you see that, think polar coordinates, okay? And the standard or classical way to do this is let x equal, this is pretty standard, a cosine theta, y is equal to a sine theta, okay? And in this case, it's your radius is 4. In both cases, your, if I can find it here, a's could be 2. Okay? Now, since you know also that x squared plus y squared is equal to 4, and that's exactly what you get by combining those two. Oh, that won't be helpful. Well, let's just plug in here. That's useless, that we've already dealt with that. This would be 4 cosine squared theta, that's the x squared, minus 4 sine squared theta, that's your y squared, plus 1 is equal to z. So here's your another parameterization. R of t would be equal to 2 cosine theta, comma, 2 sine theta, comma, 4 cosine squared theta minus 4 sine squared theta plus 1. There's your z. Okay. Now, they do something just a little bit different from that, and that's this. Notice here, this is 4 times cosine squared theta minus sine squared theta plus 1 is equal to z. But do you recognize cosine squared theta minus sine squared theta as being anything particular? Go to front inside cover of your text. The first page is blank on both sides. The next page, oh no, you're in the older, but you're looking at the right place. On one side it says algebra, and then geometry at the bottom. On the next side it says trigonometry. If you start, look under trigonometry, go down to double angle formulas. Cosine 2x is cosine squared minus sine squared. You see that? Under trigonometry, there is a left-hand column and a right-hand column. Go to the right-hand column just before you get to the graphs, and you see double angle formulas. The second one there is cosine 2 theta is cosine squared theta minus sine squared theta. So we could call this 4 cosine 2 theta plus 1. That's what the z is. So 2 cosine theta, 2 sine theta, comma, 4 cosine 2 theta plus 1. Okay. And I think that's what they got. Yeah. 2 cosine theta, 2 sine theta, 4 cosine 2 theta plus 1. They said t's. I'm sorry. I like to use thetas, but they for angles, but they use t's. Put t's instead of thetas, you got it. Same thing. So like they say, infinite number of ways to do it. Now, the problem with the first way is that you have a plus and a minus. So you really have two r's, an r1 and an r2. And that's sort of what they do here. They cut it right down here. The r1 is on this side, r2 is on that side. Okay, that's fine. They can do it that way. It's a little awkward. With polar coordinates, you just have one thing, and theta, by the way, goes from, I think, 0 to 2 pi. For instance, any 2 pi interval would work. They said t, and they said t is 0 to 2 pi. Okay. Any questions on that? Different ways to go about setting up the parameterization. Okay, let's move to example 4. I think that, here are the two functions I was just talking about. When you do it on algebraically, you get a positive t and a minus t. R1 of t is always positive in y, R2 of t is negative in y. Okay? It's 2 halves of the curve of the intersection that we saw before. But you can't write it as a single function easily because you have plus or minus in there. Okay. Now, example 4. Parameterize, to me that's such a strange word, the circle of radius 3 with its center P of 2, 6, 8 located in a plane. Okay? Circle in a plane whose center is 2, 6, 8. okay? Now, in a plane, hanging there, parallel to the xy plane. So you want a circle parallel to the xy plane. What else did they say about it? Radius 3 with a center of 268. Well, first, just imagine the circle of radius 3 in the xy plane, okay? If that's the case, this circle is going to be x squared plus y squared is equal to 9, okay? That would be in that plane. Z would be 0, okay? Now, what they're saying is now we've got a translation here. So instead of x squared, it's x minus 2 squared, okay? Plus 6 y minus 6 squared is equal to z minus 8. Or, yeah. That would be your new function. So the circle down here would be x squared plus y squared is equal to 9, r squared. That's any old circle in the xy plane, radius 9, centered at the origin. But you're moving it up here, so this would have x minus 2 squared, and here's Faith. So we're just missing Emmanuel, and he was missing this morning too. Thank you so much. Okay. All right. Plus y minus 6 squared. Okay, you've got to have the equal to 9, but you also have to have something to deal with that z. Okay? Okay, and in this notation, that's not really the best way to go. I realize that now. The better thing to do is use polar coordinates, okay? Again, your x is equal to, in this case, 3 cosine, are you using t? Yeah, they're using t's. T, y is equal to 3 sine t, and z is equal to t. Actually, z is equal to, no, that would be a helix. We don't want that. Z is equal to 0. On the xy plane, the z is always 0. Okay? Now, what you're doing with it now is a translation, and this makes a lot more sense here. Your vector, r of t, is now going to be 2 plus 3 cosine t, 6 plus 3 sine t, yeah, and 8. Okay? That would be this one, okay? Because the circle here is 3 cosine t, 3 sine t, x and y, z being 0. And what you've done is then add to that, move it up to a center there. This is the center at 0, 0, 0. Okay? So it's 0 plus this, 0 plus this, and 0 plus that. When you're moving up to that position, notice here z is always 8 here. Because it's parallel to the xy plane, so z doesn't have any variation in it. It's always 8, but it's 2 plus 3 cosine t, 6 plus 3 sine t. Okay. It would have been a lot messier to do in x, y, and z, so let's sort of forget that one. Okay. I thought it wouldn't be too bad, but it's that z part really messes with that. Okay. So we won't do that one. Okay. Now, what if it's parallel to the xz plane? Same circle, but it's parallel to the xz plane and same center. Okay? Well, now looking at that, we see that when, say, t, your parameter t is equal to 0, if you want the x to be 3 in starting there, while z is 0, well, just looking at that, I think you'd still go with x from this circle here. X is equal to 3 cosine t, z is equal to 3 sine t, and y is equal to 0. That circle right there. There is no y component anywhere. Okay? So then if you're translating it up here, the new function here, I'll call this rxz in the xz plane, this would be the vector 2 plus 3 cosine t, y is 6, and z is 3 sine, you can do 8 plus, or it doesn't matter which order, 3 cosine t. Oops, angle bracket. Okay, because that's a vector. Okay, let's see what they got. Yeah. 2 plus 3 cosine t, 6, 8 plus 3 sine t. Got it. All right. Any questions on those? All right. Let's move back. Y'all want to do the preliminary questions? Yes. Okay. So erase all that ink and let's look at these. Which of the following does not parameterize a line? Okay. R1. R1 is a function of time, or t. Okay. 8 minus t, 2t, 3t. 8 minus t, 2t, 3t. Okay. B is R2 of t. T cubed I minus 7t cubed j plus t cubed k. Okay? And C. 8 minus 4t cubed, this is R3 of t, will be 8 minus 4t cubed, 2 plus 5t squared, yuck. Goodness gracious. crammed down lunch too fast and didn't drink enough. And now I'm feeling so dry I can hardly talk. 9t cubed. Okay. Which one of those does not parameterize a line? Any guesses? C, you say? Oh, B. Actually, because your t's are really identical here, you could say let S equal t cubed. Then that would be Si minus 7S J plus Sk. And that would be a line. C it would be, because this is the third power, that's second, that's third. Can't make that all at a given, you can't adjust that in any way that all the exponents will be 1. This one they're already 1, this one you can make to be 1 by another substitution, but this one you can't. They're going to be different. So my guess would be, C, and it better be. This is 13.1, right? My head hurts. Okay, C, that's the one that can't be, that does not parameterize the line. All right, let's go to 2. I think let's clear this because we don't have lots of room to write because of the figure. What is the projection of R of t equal to Ti plus T fourth j plus e to the tk What is the projection of that onto the xz plane? What's the projection of that onto the xz plane? Well, what's true about the xz plane? Y would be 0, okay? So then we're looking at if you wanted to say it this way, if t is equal to x, then z would be e to the x, okay? Then, what is the projection of that? That would be the exponential function. How would you say it? Z is equal to e to the x. Okay? Yeah. Z is equal to e to the x. That, I think, is the curve that you would get from that. Let's see what they get. The curve Z is equal to e to the x. Good for them. Okay. Okay. I didn't write it down. I just said it, so let's do it. All right. We'll do another one of these. Bet you it's going to be a little more complicated. Which projection of cosine t, cosine 2t, sine t is a circle? Cosine t, cosine 2t, sine t. Which projection of that curve would be a circle? Any guesses? Make a guess. 3 projections, name them. Your 3 coordinate planes. XY plane, XZ plane, or YZ plane, XZ plane. Okay? Which one of those, if any, would the projection of that be a circle? I'll give you a hint of radius 1. Not much of a hint, but second? XZ plane, exactly. Because if y is a constant, or 0, forget about it, that would give you a circle in the XZ plane. Okay, let's see how they did. The projection onto the XZ plane, good for them. They got it right. All right, number 4. This is a pretty good one too. I think I'll write it down here. What is the center of the circle with the following parameterization? Okay, they're telling you this is going to be a circle. And here's its parameterization. 2 minus cosine t, or minus t, I can't read, plus cosine t, I, plus 2j, plus 3 minus sine t, k. What is the center of the circle that has that parameterization? Any idea? Okay. First, this would be something a lot like B in this picture right here. Okay? Different in certainly some aspects. Because this would be, we don't have the answer here, but remember we said this because it was circle of radius 3. Yeah, this would be 3, we called the first one cosine t, 0, 3 sine t. Okay? That would be this, z is equal to, yeah, that would be this circle. Then when you translate it out, the x comes out 2 on this one. The center comes over 2. It comes out y6 and up z8. Okay? That would then be the same circle we said with those as their constants added to the thing we had before. We had 3 cosine t and 3 sine t before, so this would be a 2 plus 3 cosine t, 6, 8 plus 3 sine t. All right. Tell me what the center of that would be then. A little louder? No, I need points. I need coordinates of a point, the circle. That one was 2, 6, 8. What would this one be? Negative 2, 2, 3. Okay? Negative 2, positive 2, 3. Now, what's that? What's the deal with the minus sign and the plus cosine? What's happening with that? Again, you're dealing with a circle here. Let's just pretend this is it. Our radius is 1 because there's a coefficient of the trig function is 1, not 3. Okay? Let's just start with the point here. Cosine of 0, when t is equal to 0, cosine of 0 would be 1. Sine of 0 would be 0. And then as you start to increase your t from 0, cosine, or the x value, is getting smaller, but the y value is going from 0 and getting smaller too. So it would be going in a clockwise direction rather than counterclockwise. That's basically what's going on. The x value is going just like you would expect, starting at 1 and getting lesser wherever you go. In fact, either direction would be going less. The z component, however, is starting at, say, 3, and since it's a minus sign, it's getting less. So it would be starting at a 1 here and decreasing, but going in this direction. Okay. That's beyond what they were asking, but I thought it might be useful to mention. Okay, the point -2, 2, 3. Okay. All right. Number 5. How do the paths R1 of t, which is cosine t sine t, okay, by the way, that is a circle on the xy plane. There's no z coordinates involved with this. And R2 of t, but now there are, goodness gracious, sine t cosine t. Okay. Now, since we're dealing with the xy plane, let's just imagine the circle here. But again, on both of these, the radius is 1. So let's just imagine that's a unit circle there. Okay. What's the difference in these two paths, these two things, R1 and R2? R1 starts out here at 1. This is 2. Forget that. 1. And starts here at y is equal to 0. And then as you increase your t, the cosine is getting smaller and the sine is getting larger. Okay? So cosine is getting smaller, the x is getting smaller, the y is getting larger. It started at 0 and it's moving out here. So it would be going, looking down at it in a counterclockwise direction. If you go over here, your x is starting at sine t when t is equal to 0. So that's going to be 0 either here or here. Let's start it here because your y is 1. Okay? So that looks correct. Now the x is going to be increasing, meaning it's starting at 0, increasing is moving this way, the y is decreasing this way, so this one must be looking going in the clockwise direction. So that's the difference, counterclockwise, clockwise. All right, which was that, 5? Okay, let's see. Goodness gracious. As t increases from 0 to 2 pi, the point sine t j plus cosine t, sine t I plus cosine t j moves clockwise, and a point on cosine t I sine t j moves counterclockwise. Okay. All right, folks. I'm going to try to finish these. I think I'm going to have to go get some water or something, because like I explained before, I gobbled down lunch too quickly because my last class went over and I'd only had 45 minutes to begin with, and I had fewer than that. I ate too fast and didn't drink anything, so I just feel totally dry. Number 6. Which 3 of the following vector-valued functions parameterize the same space curve? Okay, we got 6 curves here. 3 of them do the same one. The first one, -2 plus cosine t I plus 9j plus 3 minus sine t k. All right, I forgot my hat on the K. I knew there was something missing. Okay, B. 2 plus cosine t I minus 9j plus a negative 3 minus sine t k. Oh, man. C. Yes, in Spanish. -2 plus cosine 3t okay. Okay. A lot better. Goodness gracious. Plus 9j plus 3 minus sine 3tk. I can't write the k's right. Okay. Yuck. I left off the I here. I put the K inside. Oh, here's what we do. There. Got it. D. -2 minus cosine gotten lost here. Cosine t I, all these look alike, plus 9j plus 3 plus sine t k. Finally E, sorry about my throat. Whew. 2 plus cosine t I plus 9j plus 3 plus sine t k. Oh, I think I did it again. Sine t k. Okay. All right. I hope I got them right. This is driving my eyes crazy here, looking back and forth. Okay. We got 5 up here that says which 3 of these vector value functions parameterize the same space curve. Any you want to try to throw out right away? Sorry, that's how I approach it. Well, frankly, it's going to be a curve not unlike this one, because it's in the XZ plane, okay? Centered somewhere. Now, any of you want to throw out right off the top? Second? A? He doesn't like A, does he? Okay. Any special reason you chose A? What's that? Oh, keep it. I like keeping A. I was just going to say any you want to throw out. B. Why B? Yeah, it's minus 9J. That means minus 9 on the Y. It can't be minus 9 on the Y and the other 3 plus 9, other 4 plus 9 on the Y. That can't be the same curve. So B is out of there. Don't you think? Okay. Now we got our J's okay on all 4 of the ones remaining. Now what we've got to do is figure out which ones are going to be, and again with you, I sort of like keeping A. What else do you like about this? You like what? C? D. I like D or E. E. Okay. Why do you like E especially? On the 3s, it's looking good, because on the in the K direction, it's up 3. This one's up 3, and this one's this one's up 3. All 4 of those remaining ones are up 3. So yeah, E's not bad there. What do you notice about E? It's a plus 2 here. These 3 are minus 2. Okay. So the centers of these are the same. Minus 2, 9, plus 3. All 3 of these. Okay. That one has a plus 3, but it has a plus 2 here. Now the thing that might be bothering somewhat is that this one's a cosine 3t and a sine 3t. Is that good, better, and different? What that means is going to trace it faster, but it's still tracing the same curve. As a t or a t, as long as those are the same, this one's just going around, whereas these 2 will be going like this. It'll be going 3 times around at the same time it takes the others to go 1, but it's still tracing the same curve. So I think it's A, C, and D. Let's see what the back says. Do y'all agree, or you want to fight me on it? Okay, let's see what they say in the back. A, C, and D. Yeah, that's what we said. All right, I think that was it. Homework exercises. Do any of the odds 1 through... Wow. 1 through 15, okay? Now I would do some of each of those. I wouldn't just do maybe the very easiest one and skip it. Do some of those, 1 through 15. Then do either 17 or 19, or both if you choose. And then do any of the, or do 21. It's the only one like that. Then do 23. Then do any of the odds 25 through 31. And again, I might do a couple of those rather than just one. Okay? and then do 33, the only one like that. The other two are even. And then do any of the odds 35 to 43. Okay? And that's all you really have to do on those. However, in glancing through this, number 27, for instance, talks about Viviani's curve. Okay? You could write on who in the world was Viviani. Sounds Italian to me, but I don't know that for a fact. How did he come up with this curve? What difference does it make? And I don't know if any of you have taken any earth science before. I want to sort of say astronomy, but it really isn't that much astronomy. Basically, what you almost see here is a figure 8 type shape on a globe, and that it's not the same thing here, but it's pretty close to what we call the analemma, which is the path that the sun takes over a year, and it makes a figure 8. It's not a perfect figure 8 like this one. It's a little off, and by the way, it only goes up and down 23.5 degrees because the sun's only directly overhead, plus or minus 23.5 degrees, so it doesn't go pole to pole. But because the Earth is not a perfect sphere and is not in a circular orbit, it actually follows a figure 8 that's skinny at the top and bigger at the bottom. Okay, but anyway, Viviani's curve is similar to that. So you can write on any one feature of that or anything else you choose. Okay, any questions before we move to 13.2? I can't get the button to work. All right. 13.2. Oh, this is coming up. Let me run. That took way too long. Wish I hadn't stopped now. Okay, 13.2 is talking about the calculus of vector-valued functions, which I thought that's what we were talking about before, but actually the first one was just vector-valued functions. Now we're going to talk about the calculus of vector-valued functions. What in the world does this mean? What do we do in calculus? Two major things. What was Cal 1 all about? Derivatives. And Cal 2, pretty much, integration. Okay, we're going to do those things. And before we did either of those things, we talked about limits. Weren't they fun? Okay. Fortunately, we're going to minimize limits here. The limit of a vector value function, R of t, this is a bold R, so that would be a vector value function as parameter t, approaches a limit u, which is a vector because it's a vector value function, as t approaches some number t0, if the limit as t approaches t0 of the absolute value of the difference between r of t and u is also 0. Okay? So the limit of that difference, the absolute value of the magnitude of the difference there of those two functions, as t approaches t0, the limit of their magnitudes is also approaching 0. The difference of the magnitudes. In this case, we write the limit as t approaches t0 of r of t would be u. Okay? See, t is approaching some fixed value, t0, so that would be just some value, some vector u. It's no longer a function of t because it just has that one value, t0. Now, here would be a pictorial representation of what kind of we're talking about. Okay, here's your R of t. R of t, here's the curve along which R of t is pointing. Okay, and as t is approaching t0, R of t is approaching u. U is one function, R of t is a family of functions for different values of t, but when t is approaching t0, the R of t0 is approaching the vector u. Okay? The vector value function R of t is approaching u as t is approaching t0. Okay? Past years beyond t0, years has got to t0, there it's at t0. All right. Here's our theorem 1. Here we go again. Oh, man. Okay. Vector value function limits are computed component-wise. Thank you very much. Everything we do with vectors, it's better to do it component-wise. Remember when we're adding vectors? Don't mess around with angles and stuff like this. Add them by components. Same thing with limits. Compute those component-wise. A vector value function, R of t, which is some x of t for your first parameter, y of t for the second component, and z of t for the third component, approaches a limit as t approaches t0 if and only if each one of these functions, component functions, is approaching a limit. And in this case, the limit is R of t, as t is approaching t0 of R of t, would be the limit as t approaches t0 of x of t, would be the first component. The limit as t approaches t0 of y of t would be the second component. And the limit as t approaches t0 z of t would be your third component. The big deal here is every one of these has to have a limit. If they don't, 2 out of 3 won't cut it. They all have to have the limit. Okay. I think we're ready now for what this is part of the proof of that, and I'm not going to go through the whole proof. We need to move on. Remember what we said? This thing here, the magnitude of that had to be approaching 0. Well, they're taking that magnitude and squaring it, and this would be, and they've already talked about u being the vector a, b, c. So r of t minus u would be x of t minus a squared plus y of t minus b squared plus z of t minus c squared. That would be the magnitude of that square. Okay? Just sort of a definition there is sort of right in the middle of, well, early in the proof. Okay? Not going through the whole proof, though. Let's move on to example 1. Now, we're not there yet, but let's do it here. Calculate the limit, okay, the limit as t approaches 3, there's your t0 in this case, of r of t, vector function r of t, where r of t is equal to t squared, 1 minus t, t to the minus 1. What would you say the limit as t approaches 3 would be of r of t? Okay, that would be 9, comma, negative what? 2. Negative 2, comma. What? Which is 1 over 3. Very good. Excellent. Okay? That would be at 9, negative 2, 1/3. Perfect. Now, pretty straightforward, right? Plug it in, plug it in. Continuity, this is what I was talking about before, of vector value functions is defined in the same way as for scalar case. A vector value function r of t, which is x of t, y of t, z of t, is continuous at t0 if the limit as t approaches t0 of r of t is r of t0. Just what you would expect, hopefully. And then by theorem 1, r of t is continuous at t0 if and only if each of the components, x of t, y of t, and z of t, are also continuous at t0. Okay? Hopefully, again, just what you would expect. We define the vector derivative. Now we're getting into the calculus, the real calculus, of r of t as the limit of the difference quotient. Okay? So, here it is, right here. Now, they write it two different ways almost. The prime notation, r prime of t, is the same as the Leibniz notation, d by dt of r of t. That means the same thing. And what that means in our limit is the limit as h approaches 0 of r of t plus h minus r of t divided by h. Okay? Now, of course, what that means is this difference must be approaching 0 as h is approaching 0. If it's not, the limit doesn't exist. Okay? Even if it does, it may not exist, but it sure can't if the numerator is not approaching 0 and the denominator is. No way that's going to happen. If they're both approaching 0, then it could easily be that the limit doesn't exist, and that's what it means. Now, they also mentioned this could just be written, now of course I'll have to reduce this, as dr dt. Okay? They write it d by dt of r of t, but you know, you sort of figure r is a function of t if you're taking derivative with respect to t. So, we say that r is differentiable at t if that limit, and that right there, does exist. Notice that components of the difference quotient are themselves different quotients because the limit is r of t plus h, this part here, minus r of t divided by h. That limit right there is also the limit as h approaches 0 of x of t plus h minus x of t over h, comma, y of t plus h minus y of t over h, comma, z of t plus h minus z of t over h. Okay? Close angle bracket. Okay. Just hopefully what you would expect it to be. And by theorem 1, r of t is differentiable if and only if each of the components are differentiable. In that case, r prime of t is the vector derivative of x prime of t, y prime of t, z prime of t. Okay. It's almost time, isn't it? Yeah. All right, we're beginning next time then with theorem 2. We did a little bit. Let's see if there's an example or two you can do for homework here. Yeah, you could do any of the odds 1 through 5. I think you can do any of the odds 7 through 11. We haven't talked about second derivatives yet, but it's going to follow pretty straightforwardly from that. Well, you can stop there. Okay. We'll pick up the rest of those next time. All right, any questions? Okay, sorry I had to take a break in the middle, but throat feels a lot better now. I don't know which it was, but anyway, we'll catch you later. Yeah, and Wednesday for the other two.